Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss a new concept regarding energy correction factor. So before going to discuss this energy correction factor, first let me tell you what is correction factor and how we can define this correction factor. Then we'll go for this energy correction factor. So correction factor actually can be defined. It is a value. It is a value which is used to adjust a measurement or you can say calculation. If you are doing some kind of calculation or if you are doing some measurement, experimental measurement, okay, so value need to be adjusted. Why? To get the accurate value. Okay, to get the accurate value for that. So what is this accurate value? Now when you are doing some experiment work, okay, there some errors will be there. Okay, errors for what? That is equipmental or a setup error will be there. Okay, so number of you can say machinery equipments whatever you're going to use for experimental setup. Okay, for each setup, for each equipment, there will be some errors. So plus minus some value will be there for that. That is equipmental errors. So to adjust that value, okay, and to get it a accurate value for that, this correction factor is to considered. Okay, so I hope you understand. So or else you can define a simple term for this correction factor. So this is a value which is used, we can say, to adjust a measurement or calculation and to account for errors. In like some errors will be there for that. So to adjust that one, we used to use this correction factor. Okay, measurement or we can say some calculations. So this is about correction factor. So why this is actually considered? Because we know that the value of actual result and theoretical results, it never match. Okay, that actual result and theoretical result. Why? Because there is some errors will be there. Theoretical value and the actual value. So this will be never match. So for that we used to consider some kind of correction factor. Okay. Okay. Now you understand the correction factor. Now we'll go for the energy correction factor. So energy correction factor is nothing but I can say this is kinetic energy correction factor. We can say energy correction factor or also we can say it is kinetic energy correction factor. So here I have taken a pipe. In this pipe there is a flow is there. There is a liquid is flowing through a pipe. Suppose, let me draw another one pipe. So in this pipe, so the fluid is flowing, suppose. Okay, when the fluid is flowing, it is having number of individual particles are there, individual molecules are there. So this individual molecules, if I want to represent, suppose these are the number of individual molecules are there which is flowing in this in this pipe. So now this individual molecules is having some velocity. Okay, this individual molecules, each individual molecules having some velocity. So if you want to identify that individual velocity, okay, individual velocity of the molecules, that means in this full fluids, okay, so that will be called as a actual velocity. That is, we can say the which is individual velocity measurement, that is called as what? That is we can say actual velocity also. Okay, so let me write here individual velocity and actual velocity, we can say both are same. Okay, and it will give you values for particular that position wise. Okay, so actual velocity of particle of fluid, we can say. But when you consider an average velocity, when you consider an average velocity, so that will be different. So the average velocity will be give you that all these particles velocity average. Okay, so that is actually how to define. If you say all these particles, overall particles velocity, average pipe velocity, we can say this is also, we can say that overall particle velocity, or you can say average velocity. Okay, so if you measure individual and total overall velocity, both will be different. Okay, so this kinetic energy correction factor, what is defines, it is defined actually first, it is denoted by alpha. Let me tell you, this is denoted by alpha, and this alpha can be defined in this way: the kinetic energy which is flowing of the flow, we can say kinetic energy of the flow per second, kinetic energy of the flow per second, we can say based on the actual velocity, based on actual velocity, V actual, divided by kinetic energy of the flow per second based on we can say average velocity here. So this one is the formula for kinetic energy correction factor. So by this we can identify the kinetic energy correction factor. So this is the formula is there: alpha equal to kinetic energy per second based on the actual velocity divided by kinetic energy per second based on the average velocity. So as I told you, these both are different. So now we'll discuss how to derive or how to identify these values. Okay, so for a circular pipe, here I have taken a circular pipe where the fluid is flowing, and so let's start this derivation for this. So here the kinetic energy is flowing through a elemental strip. So here the elemental strip is not visible here, only this velocity profile is given. So the elemental strip is nothing but here a circle is there. So if you want to draw again another one pipe, I can draw like this. So this is the pipe is there, and here the liquid is flowing, and another one cylindrical element we can consider here. This is the cylindrical element, and suppose you can say like this, and the small elemental strip what is taken there, this is the outer circle, and which is radius R, capital R this is, and this elemental strip what we have taken the cylindrical part, that part is given. Another one circle what was drawn here, and another one circle, this one elemental strip as I told. So this depth or this thickness is delta R, which is given here, and the height of this is nothing but R is there. Okay, so radius R and this thickness is dr, very small is there, this one. So the flow through this elemental strip, this one, the flow through the elemental strip we need to consider here. Okay, so now I can say the kinetic energy. So let's start. The kinetic energy of the fluid flowing through the elemental ring, you can say the kinetic energy which is flowing through the elemental ring with a radius of R, and with a thickness of dr, or you can say with a width of dr. This is width we can say, and this is our radius. Okay, small r. Now what we can write per second we can write half mv square. So here m into v square u square I can write. Here the velocity u, let consider. Now mass of the fluid, we can say mass of the fluid is this is kinetic energy, but when you talk about the per second, so I can write here half mass per second. So mass per second into u square. So mass per second is nothing but mass flow rate we can say, and this one we can also write half into, so mass flow rate is nothing but we can represent in terms of discharge term also. Okay, how to denote that one? Mass flow rate we can write rho AV, and rho AV we know that this is discharge, so we can write Q. So here if you see, the elemental strip is very small, so this Q I can write a small one, that is dq. Okay, so this one I can just write rho dq. So the same value I will put it here, so half into rho dq into u square. Okay, so again if you want to write this in terms of area and velocity, this one, so similarly also you can write, so that is, let me write here, half into rho into dq I have written, and rho dq u square. So again we can write rho into dq place I can write AV, area into velocity. So area you can write velocity, what is there, velocity is there as usual, u is there, so I can write u, and area I can write here 2 pi r dr. Okay, so 2 pi r dr is nothing but the perimeter and the thickness. So thickness is already dr, and the perimeter we can consider 2 pi r. So this one I can write 2 pi r dr into, again, u square is there. Okay, so now this 2 can be cancelled, and here we can write this kinetic energy of the fluid. We can write, if you see, rho pi, rho into pi, this is r is there, rho pi r, this dr is there, uq, so into uq into dr. So this one we can give a equation 1. Okay, so this is the kinetic energy per second, okay, when the liquid is flowing, this one. So now we need to find out the total actual kinetic energy. So let's find out the total actual kinetic energy, okay, of flow per second, of flow per second. So this also we can write in terms of the same thing, what is there when you are calculating for the total actual kinetic energy. So this equation, kinetic energy, what we got, we need to just integrate this. So integrate of what? Now we can do with the integration of this equation, we need to take the limit also, so I'll tell you that one. Now let me write rho pi r uq into dr, and integration, what integration, we need to consider from this point to, you know, the total energy, as I told, total actual energy, that means whole pipe, what is the velocity is there or kinetic energy is there, that we need to consider. So that one we can consider from 0 to r. Okay, so now we need to just integrate of this. Now what about this u value? Rho is there, constant, pi is there, constant, I can take it out. And what about this u value? Now u is the velocity, u is the velocity which already we have discussed in the previous videos. Okay, if you know that one, there I have taken the values of u's. So this is the actual velocity u, the value actually 1 by 4 mu minus dp by, that means del p by del x into r square, capital R square by small r square. So this is the value of u. So we just need to put this value of u in this equation. So once we'll put the value u, then what we are going to get. Now let me write this value, integration 0 to r, and here I can write pi rho r into u is there, pi rho r into uq. So in place of uq, I just let me write in the square bracket, so 1 by 4 mu minus del p by del x, this is r square, capital R square minus small r square, bracket close, and whole q if you see into dr is there. So with respect to this dr. So these things we need to solve it. Nothing is there, only integration of these terms we need to do. So just we will start this one. Now what are the constant terms are there, we will take it outside. Only this derivative integration parts are there with respect to dr, that will keep inside. So let take it outside. Pi rho, as usual it will become outside, and with respect to this we can write 1 by 4 mu. 1 by 4 mu also we can take it out, but it will be q is there, so let q part will solve it later. So let first take it out, 1 by 4 mu, and this is minus del p by del x bracket close whole q. Okay, again inside the integration what is there, 0 to r, 0 to r, what are the terms are there here, inside part r square. So let me write r square, capital R square minus small r square, into this r is there. Okay, so r into dr. So these are the terms are there. Now if you see, again whole q is there also, so that also you need to write this one, you can write in the bracket whole q. Okay, now let's solve this part, because now two parts are there, this is one part, this is another part. So let's write pi into rho, and this is bracket start, this is 4 to the power q, so we'll get here 1 by 64 mu q, and this is again del p by del x whole q, and this is, you can say, so now here bracket is not required, we can just omit this bracket because there is no use, already we have whole q you have done here. So now next what we'll do, integration 0 to r. Now r square, here rq is there, and so we'll do one thing, this is a square minus b square, not like that, we'll take this is a and this is b, and this one we can consider a minus b whole cube. So what is the formula for this, we can write a minus b whole cube, we can write aq. So aq will be like r6 minus a cube minus b cube, this is minus 3a square, 3a square b, it's not small r actually, a square b, plus we'll get 3ab square, this is r 3ab square into dr, r dr. Okay, this is a minus b whole cube we have taken here. Now again we can write here this value, this one let finish it in this way, pi into rho divided by 64 mu cube, pi rho 64 mu cube whole bracket, just use this value, del p by del x cube. Okay, so this is the term, like means in this there is nothing is there to reduce in this value, so now we need to focus on this value. So what I'll do, I'll just first this part I'll just solve it here, so final value I'll just write here. Okay, so what is the equation for this, now r to the power 6 is there, so integration 0 to r to the power 6 into small r minus r to the power 7, and here it is minus 3 r to the power 4 into r cube, just to multiply this r inside, plus 3 r square into r to the power 5, this is whole bracket close dr. So now we need to do the integration of this. So once you do the integration of this, so what we are going to get here, now r to the power 6, okay, r to the power 6, and this r integration of r dr, so r square by 2. So what we will get, just I'm writing this value only. Let square bracket start, integration done, and we'll get r to the power 6 constant term, let it out, and this is r dr, so this is r square by 2. Okay, next similarly this is r to the power 8 by 8 minus 3 r to the power 4 is constant, let's take it out, and r to the power q dr, so this is again r to the power 4 by 4, and plus 3r square is constant, let's take it out, 3r square r to the power 6 divided by 6, integration close, that bracket is closed. Now 0 to capital R. Now just we need to put the value of r, capital R, in the place of small r. Now if you put this value, what we are going to get, r to the power 6, again r to the power square here, that means r to the power 8 divided by 2 minus r to the power 8 divided by 8 minus 3 r to the power 8. See, all these things will get r to the power 8. Okay, now here also 3 r to the power 8 divided by 6. We need to integrate of this. That's why we need to solve this value. Okay, we can do the LCM of this. So 2, 4, 8, 6. So all these things, if you take, what will be the LCM will be there? We can go for it 24. Okay, so 24 means let's take it r to the power 8 common, then we'll get here 12 minus, this is 3, and this is minus 4, 6, 18, and this is again we're going to get 6, 4, 12. So how much we are going to get here? 12, 3, 18, 12 divided by 24. So if you solve this, 12 is going to cancel, so minus 18, and this is minus part is there. So how much we'll get? 21. Okay, anyway, let's write r to the power 8. You can write like this, 12 minus 3. So okay, sorry, I'm not, it will be not cancelled. Actually 12, this is positive, sorry. Okay, now 12, this is minus term, this is plus term only there, so this is 24, and this one 21. So that means 24 minus 21. Yeah, mistakenly I have done this one. No. So now we can write how much we are going to get. Now r to the power 8, this is 24 minus 21, this is 3, so 3 by 24, so r to the power 8 by 8. So now here I am going to write r to the power 8 divided by the whole terms I have done here, and I am writing this value here. So this one we can write another one, equation 2. Okay, so previously we got equation 1, and now this is equation 2. This is kinetic energy for the actual kinetic energy, that one. Now we need to find out the average. This is kinetic energy actual. Now we need to find out the kinetic energy of the flow for the average velocity. So similarly again we can write, this is kinetic energy average part. So let's write average of this equal to, again same formula is going to use, half into mv square. Now here in place of v, again just that u I can write, now here I'll write m u bar square. That means that is the average velocity. So for this also again I can write this value per second we need to consider. So similarly mass flow rate per second we can write here, again the same concept is going to use. So this is rho ab again, so v plus we can write average velocity into, this is already average velocity is there, that is square. So you can write, if you write this kinetic energy of this value, so total how will be there, a half rho a, and this is u bar q. So this kind of concept already previously we have discussed many times. So this is the final one. Now here if you see area, and this is the average velocity. So area of this flow we can consider this is, we need to consider the cylindrical object here. So we need to consider, this is area is pi r square. Okay, area is pi r square, and this u bar is the average velocity. So average velocity actually while solving this when the fluid is flowing through a circular pipe, and what is the average velocity we got there, in that time we found the formula is 1 by 8 mu, 1 by 8 mu. Remaining things are same actually, only few differences are there, minus del p by del x into r square. So this is the formula for this average velocity. Now again, just we need to put this value of kinetic energy in this equation. Now see, this is the equation is there. So just put this value in this equation. So you can write kinetic energy, the average value. You can write half, this is rho is there, area plus, you can write half ar square, and this is u bar plus, you can write this. So bracket start 1 by 8 mu, and this is minus del p by del x, and this is r square, this is 4 q. Now if you see, this is the terms what we are going to get here. Now again we need to solve this. So by solving this one, we'll get the average velocity. So finally we need to find out the energy factor, that is alpha. So let's solve this one. So here I can write 1 by 2, 1 by 2. This one, if you solve this, q is there. So I'll take this, just to solve this one, that will be enough. So this whole q is there. Now outside 2 is there. Let's write 1 by 2. Okay, let's write 1 by 1. Rho a r square into, few terms are there here, that you take it to outs. That means this 1 by 8 mu whole q will be there. So that means we can write 1 by 64 into 8 mu, we can write 8 mu q. Okay, and remaining terms are there. What is that? This one. So that is minus del p by del x whole q and r square, and this is r to the power 6, 2 into 3. So we'll get this value. Now this one we can give equation 3. Equation 3 we can put it. So this is kinetic energy average. Now what we need to find out as per the formula, alpha we need to find out. So alpha is nothing but kinetic energy per second with the actual velocity, and we need to find out kinetic energy per second with average velocity. So this two value we already have, we got there. So just we'll put the value here. This is one value, this is one value, and this is another one value. Just write this value here. Now if you see this value, finally I'm going to get some value answer here. Okay, let's write this value, then we'll be get more efficiently. Rho pi by 64 mu q, 64 mu q, yeah, del p by del x whole q, and r to the power 8 by 8. So this is r to the power 8 by 8. So this is one actual value, and average value what we got here, average value is nothing but we got pi rho, this one, pi rho. More also you can come solve this one, like this is ar square what I have written, and you can write the value, yeah, pi r square. This is ar square actually, a plus we can write pi r square. Okay, this is pi. So this 2 into 64, 128. So pi rho 128 into 8 mu 8 mu q, and remain terms again del p by del x whole cube, and this is r square and this is r6, so that will be r8. Now see, all the terms are going to be cancelled here. This term total is going to cancel. R to the power 8, R to the power 8 is going to cancel. Pi rho, this is mu q. Okay, all the terms are going to be cancelled. So this is 128 into 8 is there, and here again, if you see, this 88 is going to be cancelled. Okay, now what are the terms are pending here? So I can write alpha 128, it will be goes off, so that is 128, okay, divided by 64. So the correction factor, the energy correction factor, what we are going to get, that is 2. Okay, so this is the final answer. Now if you see this concept where we have started and where it is landed there, so it started from the correction factor what we have discussed, and then we have discussed about the kinetic energy correction factor, and we have just based on this formula we started the derivation for this. So initially we have just started kinetic energy and the total actual kinetic energy of the flow per second. Then we went for the average kinetic energy per second. So based on that we got these two equation. This is one equation and this is equation, and finally we just based on the formula we just kept the value. So I hope you understand, and if you are having still doubt and query regarding this, you can give a comment on the comment box. Thank you all.